Okay, let's get started. So this is day 12 on the home stretch now, almost there. So today we're going to talk about acids and bases. So first, just as a review from yesterday, this was problem 12 on last night's homework, and it's talking about ions and precipitation reactions. This is going to be important for today. So I just want to make sure that this is clear now before we move on to acids and bases. So in this problem, we have an aqueous solution of Na3PO4 and another aqueous solution of PbNO3 and those two solutions are mixed, and we want to predict whether a precipitate will form, and if so, to write a net ionic equation for that reaction. So our first step is going to be to figure out what our ions are. So these two aqueous solutions, the compounds will split up into their ions. And that's how we're going to figure out what the potential products are. So we need to figure out what our ions are before we can figure out what new products they might form. So that's step one, is to identify the cations and anions in our two reactants, or our two potential reactants anyway. So when I'm looking at Na3PO4, even if I don't know anything about PO4, I know that sodium is +1. I can find it on the periodic table. It's in that first column. It has one valence electron. It wants to lose that valence electron, so it's going to be +1. So that means my cation from the first compound is Na+, or +1 charge. So I know that this whole compound must be charge neutral. It must have a charge of 0. So if Na is +1 and I have 3 of them, then PO4 must be -3. And so my ion from that compound is PO4 3-, which is how I write that it has a -3 charge. For my other compound, I have Pb and NO3. So NO3 is a really common ion. So on that table that we were looking at yesterday, you can see that NO3 will have a charge of -1. So it will be NO3-. So if I have 2 of those for every Pb that I have, then Pb must be +2. Does anyone have any questions so far on figuring out the charge, what ions I have and what their charges are? So we're always going to have, a cation and an anion, but we need to know what the actual charge of those cations and anions are, not just it's positive, it's negative. I want to know this is +1, this is -3, etc. Okay, so then the next step is to figure out what potential products I could have. So all I'm going to do is mix up which cation is paired with which anion. And I need to figure out what those products are, and I need to make sure they're charge neutral. So the first thing I'm going to do is Na was paired with PO4 before, so now I'm going to pair it with the other anion. So Na and NO3. These are both, this is a +1 charge and this one is a -1 charge, so I only need one of each. I'm just going to crisscross them and they're going to pair up with one of each. +1 -1 gets a charge of 0. The other one is a little more complicated. So I'm going to pair up Pb with PO4, but this is +2 and this is -3. So in order for my compound to have a charge of 0, I need 3 Pbs for every 2 PO4s. So I can't just say it's PbPO4. That's the right combination of cations and anions, but that won't have a charge of 0. So when I'm figuring out what my products are going to be, I need to make sure they have a charge of 0. Does this make sense? Okay. So then I can use my solubility rules, which you guys did a really good job with. So I'm not going to go through the details of that. That's in the video from yesterday, day 11. But what I'll find is that NaNO3 will be soluble, so it's aqueous. It's going to stay in the form of ions, but Pb3PO42 is not soluble. So it's going to precipitate out. It will be a solid. So then once I've done that, I just have to write my reactions. So my overall reaction is I'm going to start with Na3PO4 and PbNO3 2. And I'm going to end up with NaNO3 and Pb3PO4 too, which is going to be a solid, which is what I found from the solubility rules. And then I always, always, always balance my reactions. So I'm skipping the stoichiometry, but all I've done is what we did days ago when we were balancing our reactions, is I just made sure that there are the same number of sodiums on each side, PO4s on each side, etc. I'm just making sure that my reaction is balanced. Then I can split that up into the complete ionic equation. And so I'm just splitting up everything that's ions into their separate ions. So this, I have two Na3PO4s. So that's one Na3PO4 molecule has 3 sodiums, and I have 2 of those. So I have 6 Na plus ions. So I go through and do that. And then the only exception is that Pb3PO4 is a solid. It's not soluble, so I'm not going to split it up into its ions because it's going to be found in the form of a solid precipitate. And then I just cancel out the things that are present on both sides in exactly the same form. So these two 6 sodium ions are exactly the same on each side. So nothing has really happened to those sodiums. They're called spectator ions. And what I'm going to be left with is a net ionic equation, which is that my 2 PO4 anions and my 3 Pb cations are going to combine to form solid Pb3PO4. So the complete ionic and net ionic equations are what we were focusing on yesterday. The thing that's going to be most relevant today is just keeping in mind what ions exist, what their charge are, what their charge is, and then when we're sort of making new combinations of ions, we need to make sure that what we end up with is charge neutral. It has a charge of 0. Any questions on any of this? So problem set 11 had a ton of practice on this. So if you haven't done that yet, you can do that for practice. I've also posted the solutions. Yeah. Okay. So where did this 6 come from? There's a question in the chat. So this Na3PO4 is going to have 3 sodium cations and 1 PO4 anion. So I have 3 sodium cations and 1 PO4 anion. But I have 2 of those Na3PO4s, and each Na3PO4 has 3 sodium cations. So I have 2 things that each have 3 sodiums, and so that gets me 6 total sodium ions. And similarly on this side, NaNO3, there's 1 sodium in each, and I have 6 of them, so there's 6 total sodiums. There's a question about, do we balance charges or actual atoms? Those are going to be the same thing. So if you have this equation totally balanced, there's no charges involved here. They're already, in their charge neutral clusters. So if I've done steps 1 and 2 correctly, each of these is going to be charge neutral with a charge of 0. So there is no charge to balance in this equation. So I'm just balancing my atoms like normal stoichiometry. And then if I've done all of that correctly, then when I split up into ions, my charge and my number of atoms of each element should both already be balanced. Why is PO4 2-? Because I made a typo. Thank you. So this PO4 right here in the complete ionic equation and in the net ionic equation, those should be 3-. That was just a typo. Thank you for noticing. Good job. So yeah, the charge probably isn't, the charge is not balanced here because of that typo. If I had not made that typo, the charge would be balanced. Sorry about that. I will correct that before I upload the final slides. Okay, so the most important skill to get out of this for today is thinking about the charges of our ions and how they're going to combine. So today we're going to be focusing on acids and bases. So hydrogen, if you remember from when we were talking about atomic structures, its atomic number is 1, which means it has 1 proton. Its average atomic mass is just about 1, so that means it normally has 0 neutrons. And for it to be charge neutral, it has 1 proton and 1 electron. So when I form an H+ ion, I've lost that electron and I just have 1 proton. So if I say a proton is, floating around in solution, that's the same as an H+ ion. An H+ ion is literally just 1 proton floating around. It has a nucleus that has 1 proton and no neutrons, and then it has no electrons. So none of those electron shells. So it's literally just a proton floating around. So there are lots of different definitions of acids and bases, but the one that we're going to use, which I think is probably the most common, is what's called the Bronsted-Lowry definition. Don't memorize these words or these names, but just so you've heard it before, this is the Bronsted-Lowry definition of acids and bases. So an acid is a proton donor. So as an example, just because I think it's easier to see with examples, HCl is an acid. It will undergo this reaction. So if I put it in water, it will lose its proton, becoming Cl-, and it'll give that proton to the water, which becomes H3O+. So that H2O has 1 more hydrogen and now has a +1 charge. So an acid is something that will give up a proton, and assuming that it's in water, it will give that proton to the water, making H3O+ cations. A base is the opposite. It's a proton acceptor. So NH3 is a base. If I put it in water, it will steal a proton from water, becoming NH4+. So it has accepted or taken a proton from H2O, and that will leave the water with 1 less proton, so the water becomes OH-. So an acid is a proton donor. It gives up a hydrogen, and a base is a proton acceptor. Questions on that? Okay. So a strong acid is one, so this is pretty much the same idea as splitting up our ionic compounds into their ions. This is just kind of a special case where for the acid, it's specifically a proton that's the cation that goes and bonds with water. But it's the same idea as far as things have charge and we can move them around and that changes the charge of stuff. So strong acids are completely deprotonated in solution. They're deprotonated, they have lost their proton. So what that means is that if I have a strong acid like HCl, every single molecule or as close as possible will do this reaction. The HCl will be put in water. All of those HCl molecules will lose their proton, becoming H3O+ and Cl-. So HCl, if I put it in water, it's a strong acid where just about every molecule will lose its proton and become H3O+ and Cl-. So that's just the definition of what a strong acid means. If I put acetic acid, which you don't have to know what that means yet, but it's CH3COOH in water, about 1% of the molecules of these CH3COOH molecules will lose their proton, becoming a -1 charge and giving their 1 proton to H3O+. So 1% of the molecules will go through that reaction and give up their proton. The other 99% will keep it. So acetic acid, or CH3COOH, is a weak acid. Only a small fraction of those molecules will go through the reaction. So we haven't talked a lot about nomenclature or functional groups. We're going to do some of that tomorrow. But just as an example or kind of a preview, any of these acids that have the COOH group, which is this, it's called a carboxyl group. Any acid like this will be a weak acid. So you don't have to memorize this. I'm just sort of giving you a preview. This group is going to be the same wherever I put it. And so this hydrogen is the one that's going to fall off, and it's kind of unlikely to do that. And so it's a weak acid. So the takeaway here is that for strong acids, they'll completely split up. All of them will give their proton away, making H3O+. But in a weak acid, only a small fraction will give its protons away. Okay. So there are some rules for figuring out if something is going to be a strong acid or a strong base. Don't memorize this, but this is just a useful reference. So there's just a list of things that are strong acids. So HBr, HCl, HI, etc. Strong bases are group 1 hydroxides. So what that means is there's this X, which is a group 1 element. So that first column on the periodic table, OH. So a hydroxide is just something OH. Alkaline earth metals, you might remember from when we talked about the periodic table, are that second column. And so it would be XOH2. So that's these examples given down here. So CaOH2, SrOH2, and BaOH2 are all strong bases. And then the last type of strong base is a group 1 or group 2. So that's that first or second column on the periodic table with oxygen. So this is just a table that helps us tell, I have a compound in front of me. Is this going to be a strong acid? Is this going to be a strong base, or neither? So I'm going to have you practice using this table. So I have the following compounds, and I want to know if they're strong acids, strong bases, or neither. I'm going to keep you in here. I'll just give you a minute. And I just started a poll. So just look at these compounds, use the table, and see if you can classify them as strong acids, strong bases, or neither. I'll give you about 30 more seconds. Okay, great job. So I see some pretty strong agreement on all of these, which is great. So all I have to do is use my rules. So if I have Li2O, Li is in group 1, and it's with oxygen, it's an oxide. So this is X2O, where lithium is X. And so that means that Li2O will be a strong base. It's on the strong base side of my table. The strong acids are a little easier because it's just a list. So if I have HI, it's in that list, it is a strong acid. HF is not in the list of strong acids, so it's neither, but you might be able to guess from looking at it that it has a proton that it can donate. So it is neither, it's not a strong acid or a strong base, but you might be able to figure out that it's actually a weak acid. So it's still an acid, it can give up that H, but it's not a strong acid. So if I put HF in water, it will lose some of those hydrogens, but not every molecule will lose those hydrogens. So it's not a strong acid. So you wouldn't be able to tell that from the table. I'm just sort of telling you that after the fact. So it is, the correct answer was neither. And then NaOH is, Na is in group 1 and it's paired with OH. So NaOH is a strong base. Any questions on this or on what it means to be a strong acid or a strong base? So there's a question, can we go over, yeah, so the only way to know whether it's an acid, the only way to know whether it's a strong acid or a strong base is from this chart. There are physical reasons why that's true, but for now we can just use the chart. So that's for strong acids and strong bases. For is it an acid or a base, you can start to develop some intuition. For, you know, HF looks kind of like HI, it has that proton that it could get rid of. So it's not a strong acid, it's not on this table, but it's more likely to be an acid than a base. It has a proton it can pretty easily get rid of. There's a question in the chat, can you go over again what happens in water? That's a great question. That is what's on the next slide. So thank you for that. So what happens in water? So for all of these, I've just taken the 4 examples from the previous slide and I've put them with water and I want to know what happens. So I'll give you the first one as an example and I'll have you do the other ones for practice. So what I found from my chart is that Li2O is a base. So the first thing that's going to happen is it's going to split up into its ions. So nothing has happened to the water yet. The Li and the oxygen have just split up. So I have my lithium cations and there's 2 of them and my oxygen -2 anion. Acids are proton donors and bases are proton acceptors. So Li2O is a base, so it's a proton acceptor. So what's going to happen is that positive proton from the water is going to get taken by the oxygen. So that oxygen gets a proton, so it goes from -2 to now it has a proton, so it's -1. And that H2O has lost a proton, so it becomes OH-. Questions on what happened here? So a base is a proton acceptor, and so my Li2O has taken a hydrogen or a proton from my water. So I'm going to have you do the other ones as practice in groups. And just a hint that an acid is a proton donor. So it's going to give up its proton to the water. Does anyone have questions on this before I send you into groups? Okay. I'm going to send you into breakout rooms. So please discuss this in groups. I'll just give you about 5 minutes. So I'll pull you back in at like 11 or so. So go ahead and accept those invitations if you haven't already. I'm going to pause this recording. So for those of you watching this later, you can pause and practice with this before I show the answers. Okay, I think everybody's back. So let's go through it. So just as a reminder, a base is a proton acceptor. And so I had my Li2O, and it took a proton away from water so that the O became OH. So it took that proton away, making the oxygen 2- into OH 1-. For an acid is a proton donor. So that means that HI will want to give up its proton, giving that proton to the water. So if I have my HI, it can split up into H+, that proton, and the I-, the anion. And the HI was our acid. It wants to donate a proton to the water. So that proton will join the H2O, becoming H3O+. So this is the definition of an acid and a base. A base does this, it accepts a proton from water. An acid does this, where it donates a proton to water. Questions on those definitions or these first two examples? So so there's a question in the chat about if it's giving or taking protons, won't it change elements? So this is where it's important to remember that hydrogen is just one proton. That's all hydrogen is. So it's not that I'm taking my iodine and I'm removing or taking a proton from the nucleus. If that was the case, then absolutely I would be changing iodine to some other element. What's happening is H+ is just a proton. And so when I'm donating or accepting a proton, all I'm doing is moving a hydrogen from one place to another. So if I didn't have any hydrogens, then I couldn't accept a proton without changing like what element it is, because that would be like changing the nucleus of some other element. But all I'm saying with proton acceptor or proton donor is I'm just moving a hydrogen from one compound to another. So everything here is still balanced. I still have a hydrogen, an iodine, 2 hydrogens and an oxygen, hydrogen, iodine, 2 hydrogens and an oxygen. So all I've done is rearrange the bonds. So it's definitely confusing, but just remember that hydrogen has 1 proton, no neutrons, and 1 electron. If it becomes H+, it has lost that electron. So it's just 1 proton. So if I change what thing my H+ is bonded to, that is moving a proton from one place to another. Any other questions on this? So HF is a weak acid. So only a small fraction of the HF will dissociate. So most of the HF that I put in my water will just stay as HF, but some of it will split up into H+ and F-. It's an acid, it's a proton donor, so that H+ will go bond with the H2O, forming H3O+. So again, this is a weak acid, so only some of the molecules will do this, but some of them will do this. So this is what happens to those that do. And then the last example is NaOH, which is a base, which is a proton acceptor. So I'm going to split up into my Na+ and my OH-. I'm just going to move 1 hydrogen from my H2O to my OH minus. sorry, there's a typo here. So all that's happening is this should be H2O. So I end up with like the same products that I had before, but I have this OH minus, which is able to accept a hydrogen. So how do I know if it's strong or weak? That's just the table I had on the previous slide. So it's not something that you can easily just intuitively know whether it's strong or weak. That's something that we've had to measure over time. And there's like physical reasons you can start to understand, but for now you can just look at the table. So in acids and bases, only the hydrogen moves around. That's exactly right. So it's a hydrogen donor or a hydrogen acceptor. That's what it means to be an acid or a base. Sorry, so I have an OH minus here and an H2O here. So it's actually going to be the same on the other side, is that hydrogen is going to move to this OH minus. So this is going to become H2O and this will be OH minus. So right now, as I've written it, it's not balanced. I just had a typo. That hydrogen should move to the OH minus. So it should be H2O. So I'm going to move into how we quantify how acidic or basic something is. So in order to do that, we need to review logarithms, which you may be doing in your math classes, you may have seen before, but I'm just going to review it just in case. So the definition of a logarithm is that the log of 10 to the a, where a is just some number, is a. And so that's just the definition of what a logarithm means. This is base 10, which is sort of what we normally use. So if I did base 5, then I would do 5 instead of 10, but we're only going to be using base 10 here. So the log of 10 to the a is just a. So as examples, the log of 10 to the minus 5 is just like this, where a is minus 5. So the log of 10 to the minus 5 is minus 5. If I have the log of x is 7, what is x? I can just follow this formula and I know that a is 7 in this case. So x would be 10 to the 7. Does anyone have questions on just the definition of what a logarithm is? Unless someone tells you otherwise, you should assume that the base is 10. I could ask you, what is log base 5 of this? But I would have to say it. So if I don't say that, if I just write log of x is 7, you should assume that it's base 10. But it would be the same rules. So if I was doing base 5, then it would be log of 5 to the a is a. So the concept is exactly the same. But we're only doing base 10 here. And that's sort of the most common. And that's what we're going to assume if no one tells us otherwise. So just to kind of test yourself, if I have negative log of x is 3, then what is x? So just think about it for 30 seconds. So I can move that minus to the other side. So that's like saying log of x is minus 3. So x will be 10 to the minus 3. So we're going to use this in our definition of how acidic or basic something is. But this is, for now, this is just math. This is what a logarithm means. Okay. So the way that we denote how acidic or basic something is with what's called pH, which stands for potential of hydrogen. which you don't have to memorize. That's just a little trivia fact for you. And that's, how good are we at donating or accepting hydrogens? So just as a reminder, my strong acids, HCl, for example, will go through this reaction. So if it's a strong acid, I'll end up with a lot of H3O+. So I can tell how acidic my solution is by knowing how much H3O+ I ended up with. If I have a lot of H3O+, then a lot of this reaction happened. And so I can measure my concentration of H3O+ in molarity, which we talked about yesterday. And sometimes we put that in brackets. So instead of writing, 5 molar, we just put brackets around H3O+ equals 5 molar. It's the same thing. So I can measure my concentration of H3O+ in units of moles per liter. So just to copy from the previous slide, log of 10 to the A is A. So the definition of pH is it's minus the log of the H3O+ concentration. So if my H3O+ concentration is 10 to the minus 3 molar, my pH would be 3. So we have this pH scale where lower pH is acidic and higher pH is basic, which to some people is counterintuitive because there's more H3O+ in the acidic case. And the reason for that is that if my pH is 1, then 1 equals minus log of H3O+, and so my H3O+ concentration is 10 to the minus 1 molar. For really basic solutions, my H3O+ concentration would be 10 to the minus 14. So 10 to the minus 14 is much smaller than 10 to the minus 1. So higher pH means less H3O+, which means less acidic or more basic. Pure water has a pH of 7. So if I just have pure water, 10 to the minus 7 moles per liter of water will go through this reaction so that we'll end up with H3O+. So pure water has a pH of 7. If I'm more acidic than water, I'll have a lower pH, which means a higher H3O+ concentration. And if I'm more basic than water, I'll have a lower H3O+ concentration, which means I'll have a higher pH. So just as a little practice with using pH, HBr is a strong acid. That means that every molecule of HBr will go through the equivalent of this reaction up here. If I make an HBr solution that's 10 to the minus 5 molar, what will its pH be using these definitions? So I just started a poll, take a minute to think about it. My pH is minus the log of my H3O+ concentration. Okay. So most people seem to agree, but there's a good spread across the board here. So let's go through it. So the important thing to realize here is that if my HBr solution is 10 to the minus 5 molar, every single HBr molecule is going to dissociate into H plus and Br minus. And then all of those H pluses are going to make H3O plus molecules. So if I have a 10 to the minus 5 molar HBr solution, then my concentration of H3O plus is going to become 10 to the minus 5 molar. And then once I know that, I can just use these rules. So my concentration of H3O plus is 10 to the minus 5 molar. So A here is minus 5. So if I do the log of 10 to the minus 5, I get minus 5. And then I'm doing minus 1 times that. So my pH is going to be 5. Any questions on how I did that or what pH means? Okay. So you might notice that acids and bases are proton donors and acceptors. So if I mix them together, then one will give a proton to the other. So what that means is that if I put an acid and a base together, my acid is a proton donor, my base is a proton acceptor. And so I'm going to neutralize my acids and bases. I'm going to be neither acidic nor basic because they're going to neutralize each other without making H3O plus or OH minus. So for example, HNO3 is an acid and RbOH is a base. I'm just telling you that HNO3 is an acid, which means it donates a proton, and RbOH is a base. So what I can do is I can take the proton from HNO3, give it to RbOH, and so that H from my acid will take my OH from my base, and I'll end up with H2O, which is just water. And then what's left is the anion, NO3, and the cation, RbOH, from the acid and from the base. And so those are going to go together, and they will be a salt, which is like what we were dealing with yesterday. So I just have to take the proton and the OH, mush them together, I'll end up with water, and then what's left is going to be a salt. So this is neutralizing an acid and a base by mixing them together. So this is exactly like what we were doing yesterday with mixing up the cations and the anions. This is just a special case where one of the things I'm going to end up with is water. Does anyone have any questions on what I did here? So as another example, HCl is an acid and Li2O is a base. So we're going to write the neutralization reaction. So I'm going to have HCl and Li2O. My Li and my Cl are going to end up together. And I know I want H2O, but I only have one hydrogen here. So what I'm going to do is just balance my reaction. And so I'm going to take my 2 hydrogens from my HCl and my oxygen from my base, and I'm going to end up with H2O. And then what's left will be this LiCl salt. So for a neutralization reaction, I'm always going to end up with a salt, which is just my cation, my anion, and water. So the last thing we need to notice here is what's called a stoichiometric point. So you might remember from a while ago, we were talking about limiting reactants and excess reactants. The stoichiometric point is when reactants are present in a stoichiometric ratio. So in this first case, my stoichiometric coefficients are just 1. And so if I have 1 mole of HNO3 for every 1 mole of RbOH, I have my stoichiometric ratio, which matches my stoichiometric coefficients. So my stoichiometric point will be when I have an equal number of moles of each of my acid and my base. In this case, I have a 2 in front of my HCl. So my stoichiometric point will be when I have 2 moles of HCl for every 1 mole of Li2O. Does anyone have any questions on what the stoichiometric point means? It's just when our acid and our base are present in a stoichiometric ratio. Okay, so we can use that in what's called titration. So I'm going to use that second reaction as an example, and I'm just going to have my acid be a red circle and my base be a blue circle, just so I don't have to keep drawing the compounds out. So I have an acid solution of unknown concentration. So that's what's called an analyte. It's what I'm going to analyze to try to figure out its concentration. So I don't know the concentration of my acid, but I want to figure it out. So what that means is I just have a solution that has some amount of this acid in it, but I don't know how much is in it yet. Then what I can do is I can add a dye, which is going to be clear if my solution is acidic, but then it's going to change color at the stoichiometric point. So this dye we use is called phenolphthalein. You don't have to memorize that, but just so you've heard it before. What's all you need to know is that I can tell when I've reached the stoichiometric point. I can tell when my solution is no longer acidic. So what I'm going to do is I have a base. Stoichiometric point is when it balances. So it's when I have the right number of base atoms so that I'm in a stoichiometric ratio with my acid atoms. So it's when neither of them is in excess or limiting anymore. So what I'm going to do is I'm going to add base, and I'm going to see when the solution turns pink. So I will know exactly how much base I've added. So the base that I'm adding is going to be called the titrant. This is called titration. So that's the thing that we're adding to try to figure out what's going on with our analyte. And I'm going to use the stoichiometric ratio of the reactants. So there's a question in the chat. What I want to know is whether one of these is going to be in excess or limiting, or whether they're in a stoichiometric ratio. So all I'm looking at is the reactants and the ratio of my acid to my base. So what I'm going to do is I'll keep track of how much titrant or how much base I've added, and then I can use that to figure out how much acid I originally had. So what I'm going to do is I have my acid, I'm going to add some amount of base. And so if I've added 1 molecule of base, based on my stoichiometric coefficients, it will use up 2 molecules of my acid, and those will become this neutral salt that's no longer contributing to the pH. But my solution is still acidic. I still have more acid, and so my dye hasn't changed colors yet. So if I add more base, more of my acid will get used up. If I add more base, more will get used up. And then eventually, I will have added enough base that all of my acid has gotten used up. I've reached my stoichiometric point, and now my solution turns pink. So what I can do is I can keep track of how much base I had to add in order for the acid to get used up. And then I can figure out how much acid I had in the first place. So it's not so much that it's dissolving, it's that the base is reacting with the acid to form this neutral salt. So all I'm doing is adding base until I run out of acid. And when I run out of acid, my solution turns pink. So I'm using this as an example. So what this looks like in lab is you would have a beaker full of your acid, and you would add your base 1 drop at a time, and you can keep track of how much you've added, and then eventually your solution will turn pink and you'll stop. So I'm sure that if you take a chemistry lab, you will do this at some point, if you haven't already. By the way, you can do this the opposite way. You can start with a base and end up with an acid and add the acid. It's the same idea conceptually, so I'm just going to keep using this as an example. So just to repeat one more time, all I'm doing is I start out with an acid. I don't know its concentration, but I know the concentration of this base that I'm adding, so I can figure out exactly how much base it took to neutralize all of my acid, and then I can figure out how much acid I have based on that. Does anyone have questions on like conceptually what we're doing here? Okay. So here's an example. I have 50 milliliters of an HCl solution where I don't know the concentration. So I know I have 50 milliliters of my HCl solution, but I don't know what its concentration is. I have NaOH, which is a base, and I know that it has a concentration of 0.5 molar. I add that base until I reach my stoichiometric point. So the solution is neutralized after I've added 25 milliliters of my NaOH solution. And I want to know what was my initial HCl concentration. So what I can do is first write and balance my neutralization reaction. So I have HCl, which is my acid, and NaOH, which is my base. I'm going to pair my chlorine anion with my sodium cation and end up with NaCl, which is just a salt. And my leftover H and OH will form H2O. So this is already balanced. I can check that there's the same number of everything on both sides. And so I'm done. I have written and balanced my neutralization reaction. But I have to check that I've balanced the stoichiometric coefficients correctly. I always want to end up with salt of some kind and water. The next thing I want to figure out is how many moles of NaOH did I add? So I want to figure out how much NaOH I added so that I can figure out how much HCl I had to start out with. So I added 25 milliliters of my solution, and my solution is 0.5 molar, which means it has 0.5 moles of NaOH per liter of solution. And a liter is 1,000 milliliters. So I have 0.5 moles of NaOH per 1,000 milliliters of solution, and I added 25 milliliters of that solution. So this is just a unit conversion. I can cancel out these milliliters here, and that means that I added 0.0125 moles of NaOH. So now I know how much NaOH it took to neutralize all of my HCl. So I can figure out how much HCl I had to start out with. So it took 0.0125 moles to neutralize it. And this is where it's important that I balanced my neutralization reaction, because I need 1 mole of HCl for every 1 mole of NaOH. So if I needed 2 moles of NaOH for every 1 mole of HCl, I would need to use those stoichiometric coefficients here. So this is why it's always important to balance our reactions, because later you might need the stoichiometric coefficients. So in this case, I need 1 mole of NaOH to neutralize 1 mole of HCl. So that means that I originally had 0.0125 moles of HCl. And then from that, I can figure out my initial concentration. So I had 0.0125 moles of HCl in 50 milliliters of solution. And there are 1,000 milliliters in a liter. So if I do this math, I had 0.25 moles of HCl per liter of solution that I started out with. So I didn't know my HCl concentration, but I did a titration experiment And now I know that my initial HCl concentration was 0.25 molar. I'm going to make you practice in a minute. So does anyone have any questions on how I did this?
Wait, I have a question on step 2.
Yeah.
Where did you get 0.5 mole of NaOH?
So I knew my initial concentration of my NaOH solution. It was at 0.5 molar. And 0.5 molar means 0.5 moles per liter. That's the definition of molarity. So my concentration of my NaOH solution is 0.5 moles of NaOH per liter of solution.
Oh, that's the formula from yesterday's homework, right?
Yep.
Molarity.
Yeah, so that's just what molarity means. And so all I've done here is I've taken 25 times 0.5 divided by 1,000.
Okay, that makes sense. Thank you.
Yep. And there's a question in the chat on sig figs. I did tell you guys to call me out when I didn't use my sig figs correctly. So you're right. Because I had 50 milliliters here and 0.5 molar here, I should have rounded everything to 1 sig fig. You are correct. You got me. Any questions on how I did this? Okay, so the most common tripping point on this that people make is that they balance their reaction and then they come down here and they don't use their stoichiometric coefficients. So just remember that you need to use those stoichiometric coefficients to figure out what your neutralization point is. So in this case, I only needed 1 mole of NaOH for every 1 mole of HCl. So these two numbers are the same. But that's not always going to be the case, depending on the stoichiometry of my neutralization reaction. Okay. So here is a practice. So I'm going to have HBr and CaOH. I have 20 milliliters of my HBr solution of unknown concentration. I add CaOH2, which I know has a concentration of 1 molar. And I know that my solution will be neutralized after I add 15 milliliters of that solution. So I want to know my initial HBr concentration. So you're just going to follow the same steps that I did on the previous slide. So I'm going to send you into breakout rooms. I'll give you 7 or 8 minutes. So I'll put you back at 11:50 or 51 or so. Okay, so those of you watching this later, now is the time to pause. I'm going to go over the answers in about 20 seconds when everybody gets back from the breakout rooms. Okay, I think everybody is back. So let's go over it. So our first step is always to write and balance our neutralization reaction. So we have HBr, which we mix with CaOH2, and we have to make sure that our salt has a charge of 0. So Ca has a charge of +2 and Br has a charge of -1. So I need CaBr2. And then I always need water as the other product in my neutralization reaction. So I need to balance this reaction by putting a 2 in front of my HBr and my H2O. So it's always, I know I sound like a broken record, but balance your reactions, make sure those stoichiometric coefficients are right. So then I've added 15 milliliters of my CaOH2 solution. So I need to figure out how many moles that was. So I have 15 milliliters of solution, and I have 0.1 moles of CaOH2 per 1,000 meters of solution. 1,000 milliliters of solution. So that's what molarity means. So I have 0.1 moles of my base for every 1 liter of solution, or 1,000 milliliters. So what that means is if I just plug through this math, I added 0.0015 moles of CaOH2. And here's the tricky part. So now I need to figure out how many moles of HBr there were initially. So I have 0.0015 moles of CaOH2, but I use my stoichiometry and I know that I need 1 mole of CaOH2 to neutralize every 2 moles of HBr. So I need to use these stoichiometric coefficients of 2 and 1 here. So that means that if it took 0.0015 moles of CaOH2 to neutralize my solution, I must have started out with 0.003 moles of HBr. And then the last step is just to figure out the initial concentration, which is 0.003 moles of HBr in my 20 milliliters of solution. And I have 1,000 milliliters per liter. So what I end up with is 0.15 moles of HBr per liter of solution, which means I have a 0.15 molar solution. Does anyone have any questions on how I walked through this example or titration in general? So just like with our examples from yesterday, it's really important that we make sure that everything is charge neutral. So we get our ratios of cations to anions correct so that we end up with a final charge of 0. And we always balance our chemical reactions so that we have our stoichiometric coefficients correct. And so where that Br2 came from was I know that Ca is in my second column of the periodic table, so it has a charge of +2. And Br is in my second to last column, which means it has a charge of -1. So in order for this salt to be neutral, I need 2 bromines for every 1 Ca. And so I have CaBr2 in order for this to be charge neutral. So whenever ions are hanging out in groups, they want to have a charge of 0. So if I have something that's +2 and something else that's -1, I need 2 of the thing that's -1 in order to end up with a net charge of 0. Okay, so that's it for today. There's lots of practice on acids and bases and titration on the homework. The other thing is that tomorrow is our last day of new material. On Thursday, we're going to have panelists who have taught Chem 1A in the past, so you can ask them questions. So you're welcome to just come with questions live, but I also want to compile a list of questions I can send to them in advance. So I just stuck a Google form in the chat, and it's also, I'll send it out in an announcement on B courses, and it's also in tonight's homework set. So just any questions you have, you can submit as many as you want on that Google form so that they can help answer your questions and give you advice on Thursday. So that's it for today. I'll stick around if anybody has any questions.